Bien, nos seguimos ayer.
Out in the field where the morning breaks, the tractor rolls and the dust it makes. 16 eyes on a wide open view. John Deere driving the whole day through. No hands on the wheel, just light and time, finding its way down the orchard line. From the dirt to the chip to the open road, photons carry the heavy load. This is the way machines see. Beams of light where the future's gonna be. No moving parts, just a steady glow. Lighting up the dark so the world can know. Time of flight on a country breeze. Oh, this is the way machines see. The motive steers without a sound, amid a surface turning light around. Chillers hums with a narrow tone. A tunable laser, all its own. Point cloud counts every grain of sand. 4D pictures from a chip in your hand. And Flex Compute draws the dream in code before the silicon ever hits the road. This is the way machines see. Beams of light where the future's gonna be. No moving parts, just a steady glow. Lighting up the dark so the world can know. Time of flight on a country breeze. Oh, this is the way machines see. Smaller, lighter, cheaper, clear. The road ahead is getting near. Cars and robots, fields and skies, all of it riding on a beam of light. This is the way machines see. Welcome to the meeting, join our business conversation. Optica calling and the lights are bright. June 23rd is where we're gonna go. Photonics lifting us up like a breeze. Oh, this is the way machines see. Hey, this is the way machines
Welcome to the last Optica online industry meeting before the summer break. Today's theme is 3D sensing. For the next 90 minutes, contribute to our discussion on AI-driven stereo vision, time of flight, structured light, LiDAR, and the emerging field of photonic radar. Learn how photonics is driving 3D sensing towards mass adoption while cutting weight, size, power and cost. Time now to go live.
Hello everyone and welcome. Welcome to this very special online industry meeting. We are talking about 3D sensing, and as you heard with the song, this is the way machines see. We are really lucky today because we have an integrator who is here to tell us about what they need, and then we have many companies offering part of the solution. And the magic of these meetings is that we can, all of us, work together to satisfy the demand of the end user. So let me first of all introduce myself and the team. We are Optica. We are Optica Corporate Engagement. We are an industry network of companies all over the world, and our world, our life, our passion is to connect all of you so you can do things that you cannot simply do alone. Today, we have two teams like we usually do. One, the integrator, the end user, the company that is here with a shopping list looking to fulfill it with the companies offering 3D sensing solutions, and then the enablers. The integrator is John Deere, and the enablers are the LiDAR company Point Cloud, the LiDAR company Lumotive, the semiconductor laser, heterogeneously integrated semiconductor laser, Chilas laser, and the software of Flex Compute. We are going to do magic today because all of you have to collaborate to make sure that we all satisfy the needs of John Deere. Today, we do this for free for all of you, only for one reason only, because our corporate members support us doing that. If you want to support what we're doing here, make sure that you join as a corporate member. If you are not yet a corporate member, all you have to do is go to optica.org/join corporate, and then you can join a fantastic industry network. As you heard in the video, this is our last online industry meeting until summer finishes, and then when summer finishes, and then we start back, we come back on the 25th of August, write this one down, photonics in ophthalmology and vision care. And we're going to have lots of topics every 2 weeks on different application fields such as extended reality, quantum safe, new space, quantum computing, and of course, the biggest of all, co-package optics. If you want to present, sponsor, or be visible at any of these events, please contact us and we'll do our best, our very best to make sure that your brand, your company, and your needs are showcased in this online industry meeting. For those of you who want to meet face to face, and I prefer also face to face, all of us are meeting in Malaga on the 24th and 25th of September at the Global Photonics Economic Forum. If you have not reserved your seat yet, we have a limited amount of seats at this event. Please register as soon as possible. Do not complain if 1 week before the event there are no seats, because I do what I can, but we are of course overwhelmed by the demand of the industry. Also, on the 21st and 22nd of October, we have our PEC Photonic Enabled Cloud Computing event. And on 9 and 10 of December in Paris, we are meeting to discuss one of the most important topics in photonics today. In the current geopolitical situation, it's important to understand what photonics does for defense and aerospace. Also, I would like to say one more thing before I leave the floor to Olga. This meeting is live streaming YouTube. So let me say hello to the YouTubers in the world. Hello, YouTubers in the world. If you have any question or comment, just please write in the chat and I will read in the room. And this, of course, also valid for the people here with me in the Zoom room. This is an interactive meeting. It will be as good as you want it to be. So write in the chat what you do, what company you come from, interact to each other in the chat. The most important thing that we want to do in the next 90 minutes is to make sure that all of you find a potential partner, supplier, customer, investor, or maybe somebody to hire. And with this, I would like to give the floor to the person who put together this fantastic agenda and who's been doing a fantastic job leading Optica, this optics design, optical integration, and even optical instrumentation. Dr. Olga Ras, the floor and the attention of everyone is yours.
Thank you, Jose. Thank you for that was a very energetic introduction as always. And yeah, I'm happy to welcome everyone to this meeting, as well as our speakers, as well. For sure, I would like to thank our support team. It's from the Optica Tulsi Patel and our IT service, Nico Miller. So without them, we wouldn't be live today. And so let's start. This meeting is actually a little bit of the review of another meeting that happened 2 years ago. And 2 years ago, the situation was totally different because the entire world was very, very hyped about LiDAR. LiDAR, especially for the automotive applications. And now, since 2 years later, let's see, the situation looks slightly bit different. And we decided to revisit and see what has changed and what is the future of the technology and generally for the 3D sensing, because it seems that the big promise that was made for 2-3 years ago didn't hold to the reality. And I would like to also, if in this respect, we're also invited to revisit one of the speakers from 2 years ago, who is the Zach Boniface from John Deere. Already back then, I told him, Zach, you were a little bit, you had your thoughts on the how realistic all of this is. And I see that 2 years later, it's interesting to see what you think now and what especially you see, how you feel this field will develop in another 2, 3, 5 years. So I will welcome to the floor our opening speaker, Zach Boniface from John Deere.
Thank you, Olga. By the way, I really enjoyed that AI-generated song. That was a real treat. I think you guys have a hit on your
We'll send
hands.
you the copy. We'll send you the copy for your Skype. Not
Yeah,
Skype,
yeah.
how the Spotify.
That would be great. That would be great. All right, Olga, are you seeing my slides?
Yes.
Okay, wonderful. I'm going to start by giving maybe a little bit of perspective on how we use 3D sensing at John Deere. And then I'll talk about kind of the potential that we see or really what's important to us when it comes to the various 3D sensing technologies.
You jumped off the sharing.
Yeah, I saw that. Hang on here. Sorry about that.
Happens. We see it crystal clear.
Okay, great. Now if I could just get my slides to advance them. Okay, there we go. So at Deere, we've had 3D sensing on our equipment for about 10 years now. And back in 2010, I embarked on a project to deliver a system that would use a stereo camera to automate the transfer of grain from a harvesting machine to a trailer. And I was given 2 years to accomplish that task. And it only took me 5. Okay, so that was a joke, by the way. But since then, we've seen an explosion of perception sensing on our equipment, and much of that is 3D sensing based. And we use perception sensing in every step of our growing cycle for broadacre farming, but I'm really going to focus on just the 3D sensing applications for this presentation. So I'm going to start with the prepare step, and this generally means tillage. So what we're trying to do here is to turn crop residue into the ground so that that residue will decompose and become organic matter for the next crop. And we now have an autonomous tractor that does this tillage step. And the autonomy system includes 16 cameras for obstacle detection. It has 4 cameras on all 4 sides of the roof of the tractor. And these 4 camera setups are really, a multiple view geometry system that goes beyond, traditional 2-camera stereo vision. Step number 2 is to plant. And the planting depth and the consistency of the planting depth can have a big impact on how much food gets grown and harvested at the end of the growing season. So farmers are very interested in knowing that the seeds are going in at the desired depth. So to measure that depth, we've developed a camera that uses structured light. And based on the shape of a laser line that's projected onto the ground, perpendicular to the furrow, we are able to sense the depth of that furrow. The third step is to nurture the crop, and we do this by fertilizing and killing weeds and pests that are going to compete for water, nutrients, and sunlight, and prevent the crop from achieving its full potential. And for that, we have, again, a stereo camera that looks out in front of the self-propelled sprayer to sense the crop rows and to guide the sprayer down the row without running over the crop. And then the last step is harvest. And we use stereo cameras in a couple of different ways in the harvest step to make the farmer's job easier and more productive. First, we use stereo cameras to automate the transfer of grain from the combine to the grain cart. And second, we use stereo cameras to look out in front of the combine to see how much crop the machine is about to ingest. Okay, and that enables us to automatically optimize the speed of the combine. So come harvest season, it's not uncommon for farmers to harvest 16 to 18 hours a day. And this makes the machine much, much more productive. So, Deere doesn't just make equipment for large acre farming, and 3D sensing is becoming more integrated across all of our market segments. And all of our markets have something in common, and that is the scarcity of qualified labor or the availability of any labor whatsoever in these kind of remote areas where a lot of these tasks are taking place. So all of our customer segments are asking for autonomy or at least smarter machines to help them get their job done. This is happening in our turf business, and this is an exciting development because we make these machines in pretty high volume relative to our big tractors and combines or construction equipment. When it comes to construction, there are at least 1,000 different ways, I think, that 3D sensing can improve our equipment. But I'll give you a couple of examples of what we've implemented thus far. The first product I will highlight is a system we call Smart Detect. So Smart Detect uses a stereo camera to detect obstacles behind a wheel loader. And wheel loaders drive in reverse a lot. And construction work sites can be rather chaotic. So a system like this can really improve work site safety. The second product I'll share helps our customers that move dirt for a living. So one of the common tools for moving dirt on a work site is called a scraper. And we offer a system that uses a stereo camera to measure how much dirt is being moved in each load, and cumulatively, how much dirt is being moved over the course of a day. And then orchards are a market that have been the earliest adopters of autonomy, I would say, and we have two autonomous orchard offerings. The first is a conventional tractor that will tow a blast sprayer. And then the second is a purpose-built, self-propelled, autonomous blast sprayer. And that machine was originally developed by a company called Gus that John Deere recently acquired. And both of those machines heavily leverage LiDAR sensing. So when it comes to these various 3D sensing technologies, I'll start with cameras. And there are a couple of things that we really value in an image sensor. We do a lot of complex multiple view geometry to sense depth. So global shutters are strongly preferred to rolling shutter for that reason. And at the same time, we work in very challenging high dynamic range conditions. And global shutter and HDR is a hard combination to find, but that is something we are definitely interested in. When it comes to LiDAR, my criticism over the years has been that it's always been rather expensive and quite poor at penetrating the thick dust that we tend to see in our environment. So that really, really has limited the utility of LiDAR. Now, that said, I think the emergence of LiDAR at longer wavelengths can improve dust penetration, so that's helpful. In some, but not all of our applications could benefit from LiDAR with extreme depth accuracy. That's hard to find. We're also very excited about the emergence of FMCW LiDAR to help classify obstacles as either static or dynamic. That's very helpful for us. And we also see FMCW LiDAR as potentially an excellent source of odometry information. Our environment, as I've said in the past, is extremely harsh from a shock and vibration standpoint. So LiDAR needs to be designed with our environmental requirements in mind. And then when it comes to cost, I'm really encouraged by what I've seen in the past 2 to 3 years. And the cheaper that LiDAR becomes, the more we're going to use it. Mm-hmm. And I know this is an Optica meeting, but I would be remiss if I didn't talk about radar. It's really the only sensing technology that we can rely on to penetrate thick dust. But then we have to live with the resolution of radar, which is, of course, going to be orders of magnitude lower than LiDAR. And also, most radars that are out there are really designed for automotive use cases. Those radars do not work well in our environment. And we have lots of use cases that could benefit from radar. So the radar tech needs to be adaptable to a lot of different use cases and designed with our application requirements in mind. Mm-hmm. That's all I had, Olga.
Thank you very much. That was a quite rough overview. And to kick off, the conversation and to give all the audience a little bit of a moment to get their thoughts together for questions. So you've mentioned quite a few applications. Where do you feel that, okay, in which, because you do an orchards and turf and also construction, where in which maybe particular application is now currently the most challenging one, and where exactly the 3D sensors fall short there?
Yeah, that's a great question. I think everything that I've talked about, is now, right? Certainly, there's a lot more applications that are under development that I'm not going to speak about here in this forum. Yeah, and they all have their challenges, right? Even the products that we have in the market. But I would say, just in general, the ability to operate in all environmental conditions, right, is I would say a common thread between all of the applications.
Mm-hmm. If we think, if we meet with exactly with the same meeting in 3-5 years, what do you think will be, what are your shopping list of the improvements in 3D sensing techniques for these 3 to 5 years? You've mentioned that in the last 2, they already have done a lot, and you're optimistic about capabilities of FMCW or longer wavelengths. So for the next 3 to 5 years, your shopping list of wishes, where does the 3D sensing has to improve?
Yeah, absolutely. Again, I'm going to reiterate, when it comes to image sensors, HDR, global shutter has a lot of value, right? And I think that's an overlooked opportunity for image sensor manufacturers that has not been adequately exploited. When it comes to LiDAR, really excited, I would say, again, about the FMCW LiDAR and the potential impact of integrated, the ability to scale these LiDARs and drive the unit cost down to something that is more palatable for OEMs like John Deere. So pretty excited about that. And then, there is this space sort of in between LiDAR and radar, and I think maybe you alluded to that a little bit in the intro. Interesting to see what happens there in terms of exploring that space in between LiDAR and radar.
Actually, one last question from my side before we go to the audience, because I'm really curious. Because when you see one thing, when you see a car and you think that, okay, you know a little bit the price range of the automotive, but when you see one of your machines, the let's say the entire equipment is much more expensive. Are you still exactly sensitive to the price point of the sensing technology as the automotive, or do you allow yourself a little bit more freedom?
Well, certainly, yeah. I mean, I would say in terms of what we can afford, it's probably, proportional to the cost of our equipment. But I would also say that the price of a lot of these components has still been prohibitive compared to the value that the customer is looking for, right, in their solution, right? So there's only so much that we can charge for these solutions, right, before they no longer provide value to the customer. So, yeah, there's certain price targets that we have to hit in order for these things to make sense.
Thank you for your comment. We have, and I will call now all the questions from the audience. From the Chilas, Dmitry, you have a question about for the spectroscopic touch to
Yes,
this.
thank you. Thanks for the very nice presentation. It's really impressive of what kind of imaging systems you have put on all these machines. In the Netherlands, they also are very playful with these toys. So I quite often see them playing in the fields here in the Twente area. There's a lot of agriculture.
Yes, the farmers there are very progressive.
It's impressive. It's really nice to see this high tech. Really nice. I was curious. I recently had with another partner an idea of, for example, more spectroscopic imaging systems that you do some bug detection there going on, or there's a lot of emission regulation going on there that you do monitoring what the emissions are. So they need all special colors of lasers or light sources to address some spectroscopic features in the field. Is there anything going on in your field that you have to do some emission control, bug repellent, or pesticides concentration measurements in the field while you're on the field?
No, but we do use spectroscopic sensors quite a bit on our equipment. People will probably be shocked to hear that for over 20 years, we've had a near-infrared spectrometer offering that goes on our self-propelled forage harvesters to measure things like moisture level, protein, starch content, fiber content, things of that nature. So yes, we're always very interested in measuring properties of the crop, really throughout the growing cycle. Those are valuable agronomic insights. It does get a little bit challenging, though, when you're maybe not able to control the ambient lighting, right? In terms of the utility of those spectroscopic systems. But in those scenarios where we can control the lighting, there's often quite a bit of value.
Okay. Oh, good to know. Thanks.
Thank you, Dmitry. You will be soon on the presentation floor, but at the moment we have another question from the audience. Augusto Jimenez from Cognicy. Augusto, you have a question and also a comment. So maybe please unmute yourself, introduce what Cognicy actually does, and ask your question. Augusto? I'm unable to speak. Sorry. Okay, then I will read it out. So DTOF is more robust to scattering media than FMCW. FMCW loses coherence very quickly. What kind of resolution and range would be required for John Deere?
Yeah. Let me just say that what he said about FMCW and versus DTOF does not match my experience. the second thing I'll say is that we have lots of different applications with a broad spectrum of requirements, right? In terms of accuracy and resolution. I would say for the vast majority of applications, the more resolution, the merrier, right? But for especially like in autonomous type applications, we do have other, automation applications though, where we're looking for extreme accuracy. I would say, in the centimeter range, right, in terms of absolute accuracy for range. Yeah, I would say that's probably our most stringent requirement.
Mhm. Augusto,
Sorry
are you
to
happy with an
interrupt
answer?
here, Olga, but Zach, you just said that that DTOF is not more robust to scattering media than MNCW? Direct time on flight.
I would say just in
I would say
terms of
it's
the
more robust.
ability to penetrate the dust that we observe in our environment.
Are you
Now,
using direct
that's
time on
probably
flight?
now how much of that is a function of, DTOF versus FMCW? I don't know. It's probably more of a function of the wavelength. But yeah.
I think we are comparing, of course, apples and oranges. But I think the killer question here is you said very clear that the LiDAR is just not good enough when you have dust. And I like that very much. The statement is very much clear to me. But what is the solution? And most important, what do these people in the room need to do to satisfy a solution for you?
Well, I would say, every bit of improvement in dust penetration adds value, right? So, certainly as the wavelengths get longer, right, we would expect to see better and better and better dust penetration.
Mhm.
The other thing I would say, is there is a large spectrum, right, in between LiDAR and radar, like I said, that is largely unexplored, shall we say. I think we're starting to see more exploration of that space, and that might get us to a place where we have at the same time the resolution that we need, as well as the dust penetration.
Henrik Madsen is the CEO of SPIO and has exactly the same question I had in mind, but I think the question will sound much better if it comes from him.
Yeah.
Henrik.
Hello, Zachary. Yeah, you're teasing for longer wavelength. Can you reveal some range of the wavelength for that?
Wavelength for what exactly?
The measurement, the distant measurement. Yeah.
I can also rephrase the question in a different way. What kind of size of the particles you're dealing with, because that's going to define more or less what wavelength it's going to go through.
Yep. Absolutely. So, yeah, I don't have my numbers with me right now, but my recollection in terms of, kind of coarse dust particles, tend to be maybe in the 2 millimeter range, right? That would be kind of extremely coarse dust particles. Yeah, so that's really what probably the worst case scenario that we're trying to penetrate.
Okay. I also would think because I will throw this word into the discussion because it's thrown into any discussion nowadays, because a lot of the sensing now is also starts to improve the sensitivity or the quality of the data, not because of the sensor, but because of the data processing and how AI basically, or machine learning, let's generally say, is able now to interpret the data. Are you also looking into this direction? Maybe let's stop to improve the sensors and let's start think more carefully what we actually do with the data that we harvest.
That is really an excellent question, Olga. And certainly we've been, I would say, very much on the cutting edge of deploying machine learning on our equipment. Okay. We're very, very expert at that. But most of that know-how and experience is really related to image sensing. But I'm also very excited about the potential of machine learning to be applied to radar signals and potentially LiDAR signals as well, especially the more like the raw waveforms, essentially, right? I think the rawer the data, the better the AI is going to be able to coax out insights, right, that we can't get from conventional signal processing. So that is also a direction, I'd like to see some of these sensor technologies go. So make a really good quality sensor and then find a way to expose those raw sampled waveforms through your interface, over high bandwidth interfaces.
Okay, I think there was then this was for me also the an interesting transition to introduce the next speaker from Point Cloud.
Augusto is back.
Okay.
Speaking. Sorry.
Thank you so much, and sorry for not being able to speak earlier. But my comment about the FMCW versus the direct time flight is, with respect to the wavelength itself, they are very close. FMCW, sometimes people are operating at 1550, and LiDAR operates at that wavelength as well. But at that kind of between either near infrared to shortwave infrared, there's very little difference in the wavelength. So from the particle perspective and the signal penetration perspective, I think they are similar. My comment about DTOF being more robust is mostly about coherence. FMCW relies on coherence. It's very difficult to maintain the coherence with targets already in a clear day. And then with the dust and all the scattering from the media, that's what my comment was about. And DTOF is just rely on the signal penetration itself. But I think the comment is mostly also looking into the way to expose the scene. Typically LiDARs, especially automotive LiDARs, the spinning LiDARs, you have very few laser pulses per position. So the spinning is very quick. So your chances of collision, the light collision and losing that reflection is very high. My comment was mostly about different operations, maybe global shutter, flash mode operation in DTOF, longer exposure, many more laser pulses. You actually be able to cope with that scattering media. And I'm wondering, technologies like that is something that Cognicy is working on. It's something that doesn't exist today, non-scanning in a high resolution. And I'm wondering, about the resolution and range that John Deere is looking for. And I understand your answer.
Range is probably easier to answer, right? We don't need extremely long range. Most of our applications, 50 meters or less is really what we're looking for. Nothing compared to, what would be required for automotive, I would say. Again, resolution would be highly variable. Now, one thing that we could do, right, is we've actually constructed a dust chamber at our facility in Fargo, and if you have a theory or a system that you want to test, let's talk about it and do a study in our dust chamber.
That sounds great. Yeah.
Zach, I remember that was the same invitation to Luminar, was it, 2 years ago? We have a dust chamber. Come and try.
Yeah, absolutely.
Augusto, what does Cognicy do? Couple of words about yourself.
Yeah, so Cognicy is developing a in-pixel signal processing, so histogramming on the pixel. So basically a miniaturization of a LiDAR technology in a solid state within each of those pixels. So pixel can range from, it can cover from 10 to 50 meters as the requirements, the typical requirements for mid-range. And what we usually do is that this pixel is very small, it's in 10 micrometer pitch, and it can produce the full resolution or full histogram within the pixel itself. So we can create arrays that are small for very, very small applications, or very small resolutions, or even going to the multi-megapixel resolutions, all depending on the power consumption and so on. So really bringing the direct time of flight into solid state, very compact, in flash mode is what we are targeting.
Okay, thank you so much.
Olga, we have a question in YouTube, so allow me
Oh,
to
wow.
read a question from Zachary Boniface. This meeting is live streamed on YouTube, so those YouTubers in the world, please write your questions in the chat. Zach, the question is from Simon, and he's interested in thermal cameras. They say that they have seen huge interest in automotive for new applications of thermal cameras lately, and they're wondering if you have seen the same and if there are certain business cases for new applications in thermal cameras.
Yeah, certainly. Thermal is something that we're interested in as well. I think the key for thermal is going to be that sort of like the temperature resolution, right, of the thermal cameras in our application space. That's going to be the most important quality of the thermal sensor.
And with the so much basically data being produced and independent of the sensing technique, do you do all the manipulation and data processing on board of the equipment, post processing, or how is it a live measurement, or you do process the data later?
Oh, yeah, very good question. Most of the systems that I talked about here today, really almost all of our perception sensing systems are part of some sort of control system or real-time feedback loop. So the processing needs to be done on the machine almost always.
Mm-hmm. Mm-hmm. Thank you. And I would like, with this little bridge, I would like to introduce the next speaker, who is the Remus Niculescu from Point Cloud, who is able potentially to help you to extract much more useful information from all the data that you're collecting. Remus, you are on stage.
Thank you. I'll try to share my screen. All right. So
Yes.
I think I'm just going to go quickly through sort of the introduction of the company. So we're a company. We've actually started. We've been around for a very long time. So we've started about 10 years ago. We pioneered a new technology, which is these days I think most people there are a lot of names people refer to in the literature, but we usually use coherent focal plane array technology. Some people use switched arrays or all sorts of other things. But at the end of it, it's we manufacture these chips, which are the easiest way to think about it. It's like it looks and feels like an image sensor. It's a large array, two-dimensional array of pixels, and you can think of it as each pixel as being a coherent transceiver. We essentially, by doing this, we combine two kind of old concepts. One is coherent ranging that comes from radar. It's been around for a long time, with focal plane array architecture. So what you get is the best of both worlds. You get all the advantages of coherent ranging, resolution, range, accuracy, velocity measurement, everything that Zach mentioned earlier that they would like to have. And it is a focal plane array sensor, so it's just a chip in the focal plane of a lens. So it's very similar to a camera as far as architecture. It's very simple from a system integrator perspective. It's a one chip, one lens. There is no complex alignment. It relies on reciprocity of light transmission. Light comes out through the pixel and comes back to the pixel naturally. We use silicon CMOS manufacturing, a standard process from global foundries. Everything is solid state. There are no moving parts. Sensor is just as robust as a regular camera. I will go to the picture to the right, which is showing this is a real point cloud. It's not simulation or anything like this. It's sort of a partial team picture. The guys in the lounge area of our office in Zurich. It's taken with a sensor. It's a near QVGA. It's a 352 by 176 pixel sensor. It's on a Gen 1 EVK. What you see there, it's a field of view of 33 degrees by 20 degrees with an angular resolution 0.08. This is the field of view and the angular resolution is really dependent, just like in a camera, on the lens you choose. If you go on our website, we actually recently published this sensor in a Nature paper 2 months ago. You have all the details of the sensor as well as characterization with different lenses. You can just stick different lenses on it, and it will just work like a camera typically. So you get wider field of view with less angular resolution, or narrow field of view with more resolution. So in the middle, it's sort of a list of capabilities. So while this sensor was designed for mid-range, this picture is taken at about 11, 12 meters, which we would consider very short range. The sensor was designed for 65 to 70 meters. It actually performs reasonably well up to about 40, 50. We have taken point clouds with it all the way to 125 meters. Having said that, we don't recommend it past 50 meters just because the probability of detection degrades a little bit, and also false positives are getting a little bit higher than what is reasonable for a commercial application. So also what I would mention, this is a first iteration at scale, so this is not actually a sensor. We sample some sensors. If anyone is interested to buy an evaluation kit, we do have them available for sale. This sensor is not going to go into volume production. It's only a prototype, an engineering sample. And currently, the next generation is going to manufacturing, which is a standard QVGA. It's a 320 by 240. It will have much longer range. It will be configurable to go anywhere from 60 to 70 meters, which we would consider short range, to close to 200 meters, which would be the long range. As far as I mentioned their capabilities, so in general, up to now, we've been working on an ASIC model, in the sense that this particular chip that you see in the pictures there, the bigger one, was designed on the specs of a customer. So it's an automotive customer that actually paid for the development. In general, the capabilities we have right now, we based on existing silicon, performing it in different configurations, we can do anything from short range to possibly as high as 400 meters. Resolution anywhere out to about VGA with a current pixel size. I would say that not all of these are simultaneous, so please keep that in mind. We're not going to tell you that you can get all of those 5 things in the same time. We can get you high depth precision, that essentially depth noise at as low as, if needed, even below 1 millimeter. We generally never had anyone asking for that, but if you need it, it can be done. Radial velocity as low as 1 millimeter per second. And power, again, as I mentioned, this is not for a VGA type sensor. That would be more like in the 10 watts plus range. But if somebody wants a small sensor for mobile, for consumer applications, we do have configurations on which we can go below half a watt. This is a page. This is actually at the bottom. It's like a snapshot from sort of the basics, how this works. I was mentioning, maybe I'll go through the pixel. So at the left is the pixel. For people that have a little bit of an optics background, everything is done in silicon photonics. So you see in green are silicon waveguides, and we split the light from a bus and we send it towards 2 grating couplers towards the outside world. It couples back to the same, after it bounces off the target, it couples back to the same gratings. It goes in the reverse direction and goes into the second, there are 2 detectors there, 2 germanium or silicon detectors, where it gets mixed with local oscillator, and it's a coherent receiver. And then there is a transimpedance amplifier on each pixel. And now once you make a pixel, you can see here a block that is doing the imaging. We generally illuminate a row or a column, depending on how the sensor is configured. at the same time. So it's a little bit like rolling shutter here. We illuminate a row and then we read it, then we move to the next row, we read it, and so on until we finish the frame. Now, sort of coming back to the high level, you can think of this as we essentially enable a camera-like system architecture. So it's kind of like the equivalent of a CMOS image sensor for the four-dimensional world. It is coherent, so that's the fourth dimension, so we can extract radial velocity as well. It does have all the advantages of coherent technology performance, and it has the scalability of a focal plane array architecture. Everything is done in large-scale production quality processes. So we work with global or front-end manufacturing. We work with packagers, both small and large, but we do have also already working with a volume packager. Yeah, in general, it's everything is done so it can be going into production and also have a compelling cost point, price point. High performance and lower cost, and at this point, we actually think that we do have, we're generally benchmarking against Sony's, the IMX479, and so we do think that at this point we have a lower cost than competing DTOF sensors based on just area of silicon and complexity of the process. And in some ways, we're only getting started, so we think there is a lot of room to provide this level of performance at a very, very compelling cost. And also, I would point out here, because of the monostatic architecture, we save the system integrators a lot of parts that otherwise, and alignment steps and all sorts of other things, which are a little bit painful in manufacturing. As far as I already mentioned that, as far as we can do short range to over 200 meters, we can do large sensors if you really are interested, and you have to pay for it. It's generally large sensors means also a larger silicon, just like in a camera sensor, larger amount of silicon. Of course, we have all the advantages of coherent immunity, ambient light, optical noise, and really the way we and we're actually, I mean, this is a very, very short 2-page presentation, but we're not only looking at the even our chip. So if you look at the paper, it has a lot of electronics co-integrated with the optics. So we're, as you probably see here, there is a transpieces amplifier on the pixel, but that's only the beginning. There are amplifiers everywhere on the readout. Everything is fully integrated. The switches which are being used to direct light to different parts of the chip, they have all the drivers, everything, all the electronics is on chip. The chip communicates with the digital communication interface, an SPI interface. And we're kind of, again, like we're integrating more and more parts into the chip. So we're trying to, the way we look at it from as far as cost reduction, we are doing it the electronics, the
right way. We're doing it the right way to make sure that this technology has a higher performance and lower cost compared to direct time of flight, which is what we all want to do. Before I give you the floor to Zach, so he can give us his opinion and his room for collaboration with you, Rimos, there's a question in the room coming from a company that is very dear for me. Lumotive is represented today in the room by Apurva Jain. Apurva, what's on your mind?
All right. Hi, Remus. A very, very good presentation. I think it's a very exciting technology. And I asked my question before I saw the second slide. So let me just maybe rephrase my question a bit. One, I wanted to understand what type of transmitters is your technology or this focal plane array compatible with?
Yeah.
And when you compare the cost or performance, are you comparing it for the full system or just the chip to chip? Right? So to build a full LiDAR system, you need to have the transmitters and things. I have a second question as well, Remus. Sorry. I'll just ask it together so you can answer it. And then where do you see the scalability of the technology? Because it's very exciting. Where is the technology scalability for field of view, right? And frame rates? Like what are your, where do you see this headed with this type of technology?
Okay, that's a lot of questions. So we'll try to address one by one, and if I forget, you can kind of get me back on track. So first, the transmitter. So we actually look at it. So first of all, we are a tier 1, tier 2 supplier. So we're not building systems. We are building an EVK. So it's a reference design like any other semiconductor company, but we are a semiconductor company. We have no intention to compete with, like, I don't know, IVA or any of the tier ones or any of that. So for us, those are customers. So that's one. Second, you asked about transmitter. So we're currently using an external modulation scheme. We are not married to a particular transmitter. So there are a lot of people in the industry do direct modulation of the laser. The main reason why we haven't done that, and we continue for now to do external modulation. So we use an in-phase quadrature modulator, which is built in also in silicon photonics. It's the same process. And it's actually going to be integrated with the array. We're also going to integrate the driver. So as I said, we're trying to bring more and more, all the chips that the customer or the system integrator we're selling to is normally has to buy from someone else to put them on the board. We try to already kind of integrate as much as possible. So that way we use the overall BOM for the system integrator. That's kind of how we think about it. So anyway, in general, anything that we feel like needs to be tailored or it would save cost if we bring it on chip, we're going to bring it on chip from the system level.
Yeah, we have a very similar approach as well, like because we're coming from the beam steering side. So in this case, when you're comparing kind of the DTOF versus this approach, you're looking at the system level, not just the chip level. Is that right?
Well, we're looking at the system level only from the perspective of if a part that is on the board, we can bring it in. It's relatively simple and it will save the customer $1 or $2 and we'll bring it in. If it's something that's just commodity, won't save any money, we let the customer just buy it from someone else. But we look at it from that perspective. If it makes sense, we'll bring it in and if it saves money. If not, we leave it alone. Now, coming back to your question, we're not married to the external modulation. We've been using external modulation because it actually works. It's extremely robust. And what people quite often don't understand is there are a lot of direct modulation systems out there. If your direct modulation system is not super linear, you're going to take a very serious hit in signal to noise ratio. It is very important for your transmitter to be very, very linear. And you can offset that by just throwing more power at the problem. What we're seeing now, while that was okay at the beginning of LiDAR, today is not okay. Our customers are asking us, how is your power consumption versus what Hesai is producing? So if I throw an extra 5 watts, that's not okay. So I would say that we're sticking right now with the direct with external modulation mostly because it works. It's extremely efficient. It's extremely clean. It's more complex than direct. We haven't seen yet a direct transmitter that we're convinced it will work without increasing the power budget.
Primus, you're doing a fantastic job, and you're going to hear from Apurva in a second. But let me give the floor to Henrik Madsen from SPIO, who has a very good question. Henrik.
Yeah.
Hello. I saw your schematic setup. Would it be beneficial to have some kind of a lens system that can concentrate the signal to the gratings?
Sorry, I didn't catch that.
Yeah, so you have the grating couplers to waveguides. Those grating couplers are not the most efficient in the world. Would it be beneficial to have some lens system that can deliver the beam in concentrated form to the grating, so you can have more signal?
Okay.
Yeah.
So it's actually, they're more efficient than you think. So let me just first answer so also if you look at the paper, we do have a lens there, but for a completely different reason. So the grating is actually, light is transmitted through the grating. So it's coming out of the grating and it's coming back into the grating. Grating loss is between 1.5 and 2.5 dB roughly. And this is free space. So you have to have in mind that this is not the same as coupling from a grating to a fiber because we don't need to mod match. We just need to keep it clean. So that's number one. Second, we are using a micro lens. We are using a micro lens for a very different. Okay, on the way back, maybe I should cover that first. In coherent, you're only coupling a single transverse mode. So you can think of it as a laser beam. So it doesn't, you're not actually, by collecting more light, you're actually not doing anything. You're not improving your SNR because it's incoherent. So And that scheme works in a bistatic, because there you have separate lenses, so you technically could collect more light, but it won't couple into the gradient because the only thing that matters is what's in the fundamental mode. I don't know. It's a bigger question, and it's a bigger discussion.
It's a very good question, but I can tell you one thing from the bottom of my heart. Evaluate the optics layers of SPIO for encoupling of the light. You'll be surprised because the grating couplers that you have are very narrow line width selective, and these ones have potential to do some things as well. But I would like to leave it there because now what I want to do is to go to Zach Boniface, show him this slide, and ask him, is this useful to you in any way? And what kind of feedback would you give to Remus, to Point Cloud? Zach Boniface.
Yeah, Remus, thanks for the presentation. Very, very interesting technology. Certainly would love to follow up after this meeting. Maybe a couple questions for you. So, is there a particular wavelength that this technology operates at, or is that variable?
So we're currently working at this sensor is working at 1.3 microns, so it's in the O band. We have done in the past sensors at 1.5. We kind of switched away from it because we feel like 1.3 is a better compromise from a number of reasons. I won't go into it right now because there are about 10 different reasons why, pros and cons of the different wavelengths, and we can go into it. By the way, I had a question a little bit for you, because I was like, we had conversations before with some of your customers, and they mentioned dust, and we haven't had the chance. We tested it in fog. It penetrates as long as we have enough power to penetrate through the fog. I'm assuming that's pretty much the case in dust. I would also assume that we're doing okay because of there is no blinding effect here. So in DTOF, I think on dust, you're probably going to blind the sensor, but you know better.
One way to find out, right?
Yeah, we haven't tested DTOF to see how, but we would expect that it's going to blind the sensor because you have some backscattering that is going to start getting the outline going.
It has said that he's going to follow up with you after the meeting. Yeah. That is why we are here. That is why we're here. I'm very happy. And I'm also very happy, Remus, because the company that I'm going to introduce now is a company that means a lot to me. As you know, because you see my LinkedIn, I go to CES every year. And I always try to find out the innovation, the biggest innovation being there. And the LCM component of Lumotive always calls for attention. There are year after year, always nominations of innovation awards. Lumotive is a great company. And Apurva is here. Apurva Jain is here to tell us also not that they're a great company, but also how can they address some of the unmet needs presented by John Deere in the beginning. Apurva, thank you very much for joining the meeting today. The floor and the attention of all my friends is yours.
Always a pleasure. Always a pleasure. Thank you, Jose, and thank you, Olga, for having me here again. And I'm very excited. What I'm going to do, if you guys can see the presentation, I was going to present a video, by the way, so it would be in one slide, but I'll still try to keep it within 5 minutes. Okay, I'm going to present a little bit of a systems level view, end use view, because at Lumotive over the last couple of years, what has really changed is we've really started looking at what the end customers need, and we're trying to separate, what the end customers need, and we want to address that total cost of ownership and solving their problems that are actually happening at the ground, at their operation level, right? And then we bring it back to our chip and deliver the sensor. So I'll talk a little bit about that. And I'll use a particular example, and this example is related to our success in the robotics that's happening in industrial settings, in warehouses, in last mile delivery, and kind of the industrial process automation. But the same concept expands to, we are working with, an end user for construction equipment, and they're putting the same type of sensors that is enabled by our technology for safety sensing, for 360-degree safety sensing in construction vehicles in Saudi Arabia, desert environments, right? So just taking this particular example about robots in industry, and we're hearing a lot about this, right? The physical AI layer, robotics really coming into play at warehouses and all these processes. They're becoming a common feature, and the robots are going from doing single task pre-programmed to being dynamic and being in environments that are, that are requiring the robots to do multiple tasks and closer to objects and closer to humans. Now, this is where the previous generations of robots are not very well suitable, because The robots are using multiple sensors, as Zach, you were also presenting, like your current equipment in every direction. Sometimes you use 4 to 6 sensors to do different things. Same thing happens in the warehouse, where they actually had 2 stereo cameras and 2 line scanners. So one line scanner looking at just the floor to know if there's a cliff or a fall or a step. There are 2 stereo cameras for object identification, classification, collision avoidance. And they had a long-range sensor, like 30 to 50 meters, to look at the localization so the robot can move. And imagine this in all 4 directions, right? So this is the number of sensors, just 3D sensors that we're using in addition to RGB. And we call this like a complex way of doing things, very high cost, poor scalability. Each sensor is purpose-built for just one type of sensing. And in spite of this, actually, with one of the biggest West Coast, warehouse companies, you can say, or e-commerce companies, who is a strategic investor in Lomotive, I cannot name them, particularly in this case, they had a huge operational efficiency because even in spite of all these sensors, there was a lot of gridlocks between the robots. The robots will go and catch each other. And when you look at the full animation, we have kind of mimicked it. And they would get into gridlocks because of sensor-to-sensor interference. They'll see too much saturation from the ground sometimes, and they'll think that there's a hole in the ground, and they'll stop there. Okay, or they'll get too close to some metal structures, and there's multipath artifacts, and they wouldn't know how to get closer to those objects. So humans have to interfere and unlock these robots. There was 40% of inefficiency in these operations. So this is where Lomotive comes in with their chip-based technology, LCM, beam steering technology, that allows programmable sensing. With one sensor, we can enable looking at the ground with the with the kind of the performance specs that you need for the ground. We are able to create a slice that is long range to look at your localization, and we're able to create your region for collision avoidance, all in one sensor. And this is while improving the point cloud quality, reducing the saturation, enabling a very high dynamic range sensing. By very high, what I mean is we do 4 to 5x of normal kind of laser dynamic range using our LCM technology, and enable high frame rates where you need it. So with single sensor, we replaced actually 4 sensors. So 4 went to 1 in this particular warehouse application, and we are enabling that for other kind of platforms as well. Now, this is where Lomotive is very much like a semiconductor company as well. We're building the light control metasurface LCM chip, which is an integrated CMOS chip, enabling LiDAR platforms that really end up in total cost of ownership being much lower, highly scalable for the robotic and autonomous platforms, enabling much higher data quality, especially when it comes to artifacts like saturation, like multipath, and outdoor performance, even for iToF sensors, by the way. And then adaptive sensing, enabling you to do different kind of performance in different regions of interest, and making it highly dynamic for changing and very dynamic environments, right? Now, the way we go to market is we have the LCM technology, and we have multiple partners across the industry, including people like Namuga, who are in South Korea and really focused on the outdoor robotic platforms. They're building sensors using technology with DTOF, basically SPAD arrays out to 70 meters with 120 by 90 degree FOV, and close to QVGA. That's the best resolution today, at least, available until Cognizy comes up with something else in the SPAD-based market. We also have people like Leopard Imaging, or partners like Leopard Imaging, who are building RGBD sensors. This is using an on-semi iToF sensor with 1 megapixel. We use it in the VGA mode, 640 by 480. But with the LCM technology, we're able to extend the range of iToF from typically like 5 meters. In our architectures, it's about 30 meters. So we can do 30 meters of ranging with iToF with this type of resolution. And then we are also developing several dev kits. I put an example here, which is a 180-degree sensor. So full 180 degree by 110 degrees using a single sensor. Now, this type of optical design can be applied to both DTOF and iToF. We are compatible across different image sensors. And our chip, we have, our Gen 2 chip is for 9xx nanometer. targeted for line scanning and LiDAR applications. But Remus, we also have like a 1310 and 1550 nanometer chip. So we're not wavelength constrained, right? We built that for the data center market, but also we're getting a lot of interest from FMCW companies for the 1310, 1550 nanometer chip to do solid state scanning for FMCW systems in the slow axis usually, right? But there are various things possible. So where our focus in the 3D sensing is really in the TOF, because we think that the TOF can enable the lowest total cost of ownership in the system and can be scalable using the current ecosystem and enable us to do things like this highly dynamic sensing, especially important for robotic applications where robots are in more dynamic use cases, and you don't want to have static eyes. You want eyes that can be task-based, and you can change how you see the world based on the task you're performing. And we can also scale this, as I said, to full 180-degree sensing, and we have these things coming out in the market through various partners. So just to sum it all up, we are, taking a very much of a systems approach. By systems, I don't mean just LiDAR or 3D sensing system. We mean the end platform system. So we are working closely with the partners to even integrate other sensors into the same package to really reduce the cost and make it easy to adopt, right, in the end platforms. We're extending the range of both iToF and DToF sensors to enable faster moving robots. We are enabling sensor consolidation. So one sensor instead of many saves a lot of dollars and complexity at a system level. We are solid state, no moving parts in there, ends up being reliable, at least from shock, wide, temperature range perspectives. Overall, the power efficiency is much better at a system level, both from low power sensor or LiDARs, but also less LiDARs or sensors overall in the system. We enable high frame rates that is unprecedented in regions of interest. In regions of interest, we have shown one of our customers is using 450 hertz refresh rate in a narrow slice to look at really fast moving objects on the highway, actually. High precision, this is limited largely by the iToF and DToF, but with steering and more power per pixel, you improve the precision of both of these technologies. So comparable architectures, we have higher precision, reduced noise and artifacts, especially multipath. And when you look at saturation from ground and shiny objects, and software-defined capability that really allow you to do closed-loop sensing, closed-loop learning and optimization. And one of the things that we enabled with a partner for this, the heavy equipment, is utilizing those capabilities to enable better learning models for edge AI application. So that partner, and I'm happy to actually, Zach, I'm interested in testing out your dust chamber with their perception stack, not just with our sensors, because they did develop a perception stack to see through dust in Saudi desert. And they are deploying it there in heavy equipment from Mac and Mercedes and such for their construction. So I was just there last week, and we took a lot of data using a dump truck driving in the desert. And their dust cleanup algorithm or like removal algorithm worked beautifully, right, for the 360 application. So it'll be fun to connect and see if we can bring some of that and test it out with you.
Indeed.
So that's all I had. I kept it very short and sweet so we can keep some more room for questions and discussions here.
Thank you, Apurva. I mean, Zach, you already have a little, I think, group traveling to Fargo, to your dust tunnel, so be prepared. Everyone is ready to test. I wanted to ask Apurva, so are you the similar way with the point cloud? Are you fabless, or do you manufacture something yourself?
We are completely fabless. We are also using leading semiconductor foundries. We have multiple foundries that we work with, by the way, because we want to make sure there's a multiple supply chain, right? Diversity there. So we work multiple foundries, both in Asia and North America, and same with the packaging houses, right? To package our chips. So what we sell as a product is these LCM chips that can be integrated. But just like point cloud, we do a lot of reference, so our customers can go into building their own LiDAR or integrating directly, because a lot of robotic companies or even automotive and heavy equipment companies are becoming vertically integrated. They want to build the sensors internally and integrate. So we are also working with several OEMs directly who can adopt a reference design and build their sensors and integrate it completely internally in their own kind of equipment, right? So multiple go-to-market strategies, but we do enable full system designs as a starting point. as a reference design.
Mm-hmm. So you can you would be then to collaborate with the partners, coordinate to develop the entire system together. And yeah, since you're apparently insensitive to the source, or let's say not very that you're agnostic to the source, much more possibilities open up. And I mean, Zach had in mind a very long wavelength, and maybe in this respect comes the questions: do you really have any limitations for the wavelength that you can operate at? Because you mentioned 1.3, 1.5. What it's shorter or longer, or it doesn't matter?
Yeah, for us, like we have chips that are working all the way from 900 nanometers actually down to 80 nanometers to 1550 nanometers. But we also have our views on the LiDAR market. So we do think that we're very excited about the recent developments in FMCW technology with some companies, and I think Remus, what they're doing is really interesting. We also hear about Voyant Photonics and others, right? So we're keeping our pulse on the market and seeing where those are going. But today, if you just look at today, what can be deployed at scale, we think all of those are ToF-based sensors, iToF and DToF, because the only mature 3D sensing technologies outside of stereo, which is very limited use cases for near range and what you can do, in really 3D sensing, what can go to market today. And we need to make revenue today, not 3 years from now, right? So from our reference design perspective, and to make revenue today, it is all iToF. And we think iToF is actually getting very interesting in direct time of flight, like with chips from onsemi, which are megapixel on-chip processing, and we extend the range to 30 meters. For robotic applications, we're getting a lot of traction there because a lot of robots don't work in the dust like John Deere's heavy equipment does, right? So for those type of like quadrupeds, AGV AMRs, for even forklifts, from people like Toyota and TMH and others, we're getting a lot of interest for iToF sensors, indirect time of flight sensors. And that's actually a bigger, faster growing, let's not say bigger, but faster growing engagements for us are the iToF and kind of these 30-meter iToF sensors. And then on the DToF side, there is a lot of interest in the market, but there's heavy competition from Chinese suppliers like Hesai and RoboSense, right? So we see that for the DToF market, where we are getting traction is for people who don't want to use Chinese sensors, right? Or one of these Chinese suppliers who want to extend the performance for the next. It is. But the rest of the supply chain is not there. The rest of the non-China supply chain is not there today. It's not very mature. So we are looking to see, okay, how does that market develop? Because as you said, we are from Lumotive perspective, we are very agile because we can support a lot of these different LiDAR architectures, different wavelengths, different receivers, right? So we are really seeing that, okay, where is, the need for wider field of view, for longer range, okay, and for more software-defined capabilities. That's where we can kind of really plug our component in.
Yes, you mentioned in the presentation about software capabilities. And I mean, how much, because I remember I've seen one of your amazing demos, and you also have these amazing scanning options when you can create different patterns and use them also for scanning really with the patterning. Is it, do you think, and now you rather in your presentation, you concentrated on the software capabilities. So do you think it's, let's say they are compatible, or you rather decide, okay, that we don't go anymore to the different or complicated patterns, but rather put more effort into the signal processing and the software, let's say, enhancements?
Yeah, actually, for us, it goes hand in hand, Olga, right? It is actually the software of perception software is becoming better because of the low-level programmability we offer. For example, what software programmable beam steering does is where I want to get more precision and more range, I can focus, I can make the beam smaller. So we don't just do steering, by the way. I think from our presentations, to make it better, we also have a lens function. So we can make the beam narrow or wider with our LCM while we are steering. So let's say in the horizon, you need to look farther or with more precision or longer. We make the beam smaller, so there's more power per pixel. Okay, and we can integrate longer. And now you get better data to begin with, and the perception algorithms run on better data, producing better results. And when we're looking at the floor, by the way, we can make the beam bigger. We can expand the beam with the LCM. using the patterning on the LCM, and we can, reduce the amount of time we spend there because the ground is very close to these robotic systems. It's not very far, right? So we can control the exposure, we can control the number of rows we are illuminating, and the time we are looking or spending there. Now, this is the part where it's completely flexible, that the AI or perception layer can tune these parameters in real time. Okay, so as you're going, let's say you're going through, like you're driving, in the driving mode, they're like, okay, the speed of the vehicle is such and such. I only need to look at the horizon and get from point A to point B. The perception stack will actually configure the sensors for the mode, which is, let's say, the driving mode. And when this vehicle or robot stops to do the work, it can kind of change into a different mode to interact with the surroundings or the objects, or get into a safety sense mode, whatever the desire may be. Right? So one of our humanoid companies loves this, because as the humanoids are walking, right, those things, they want to know where they're located. But when they're at the table doing work, they want to now see the objects in near range, right? So they're building a lot of this. So this actually makes us incumbent. We say, okay, we're solid state, low cost, all of that, start trying us. But when our customers' perception team starts using all of these features, that's where we become sticky. Then it's very difficult for them to now undo, right? Or not use a lot of these features. They almost come to expect that, okay, this is what we need.
Okay. Well, I hope in a few years your chip will be in one of my vacuum robots. Meanwhile, that
we really hope so. We're working towards
it stops to crash my lamps and other furniture. Meanwhile, we have a question from Remus. Remus, you wanted to ask something about the chip itself. Go ahead.
Yeah, I mean, it was just simple, like, was curious about loss budget for a single reflection, and then
yeah, absolutely. Yeah. So for the LCM technology, right? By the way, all the numbers or all the claims that I'm making at a system level, because at the end of the day, what we care about is when you enable, let's say, a 50-meter range, what is the cost to the customer to get to a 50-meter range, in both in dollars and power, right? So it's really at the system level that the customers care about. Actually, you know what? Like in the last year, this is the first time I'm getting asked about the LCM efficiency itself. Because at this point, most of the customers care about, okay, I'm getting a sensor for a range. What is the power and cost of the full sensor solution? That said, our chips actually are about 50% efficient today. So light in versus light out in the direction you want is about 50%.
About 3
We
dB.
started breaking the cost and we started breaking the cost and power budget compared to other illumination technologies for ITOF and DTOF when we were at about 35% efficient. So now any improvement we make, and we have a roadmap to get to about 65 to 70% efficiency, any improvement we make basically lowers the cost or power consumption in the system further.
Okay.
And how do I think about angular range? What's the max, what's the min, and how much do I have loss if it's depending on the angle?
Apurva, Remus, let's continue the conversation maybe off the after. We have always a little post seminar beer. Exactly, you can put it in the chat. Meanwhile, we're with the last two speakers. These two speakers, we're already building up the system. So we have a chip, we have a scanning system. Now we need a source, and we have a presenter in the room who will be responsible for the source part. Dmitry, tell us, what do you have to offer for this novel 3D sensing system that we later gonna offer for Zach to test in his dust tunnel?
Well, thanks a lot for the introduction. I think it's very, very inspiring what we're all looking at here. So share button. I think you should see my screen right now.
Yes.
So at TLS we make light sources. So I think we all need light sources in a wide range of wavelengths. And we started off in 2018 with gluing simple chips together, an indium phosphide chip and silicon nitride feedback chip into these butterflies. And then we had a tunable laser. These tunable lasers can tune over 100 nanometers tuning range and have a very narrow line width of 1 kilohertz. So that was very excellent for very small integrations, LiDAR systems, and any other system there. In 2020, we had an evaluation electronics, and in 2024, we present nowadays the light source. Here we step out the technology what we're putting up to the market, but we put a product into the market. But we can always go back to the chip tech if you want to co-integrate it into your sensor system. Meanwhile, we're expanding our wavelength portfolio. We've got our workhorse at around telecom wavelength, the C-band, which tunes a nice 100 nanometers. And we also can go to slightly longer wavelengths. This is interesting for fog applications in some cases. For dust, I don't know yet. But yeah, perhaps we should find this out in the future. And the technology around 1310 is also emerging. So we've got a new product since 1 month on the market, which delivers 100 nanometer tuning range around 1310 nanometers. We've got some specialties for some biomedical applications typically. That's why I also interested in applications where you look spectroscopic features in the field like Raman or any absorption lines in the field. So there we also have some light sources at shorter wavelengths. Yeah, where are the applications? Well, we see a ton of applications in this event that we're now looking at. But yeah, for LiDAR, there's a lot of wind LiDAR applications in the field where you want coherence length of multiple meters, so you can say something about the speed of the air in the atmosphere. There's photoacoustic imaging. There's an example of that. There's a laser pulse penetrating into your skin or wherever it is, and then there is a microphone array which is read out by using optics. And here our lasers find their way to the market to really do some 3D imaging inside your body for these kind of things. Vibration sensors, a lot of automotive applications run in this field. For structural topology, OCT, where you really want to look into the depth of your tissue or material. And then there's a lot of material science going on for fluorescence or Raman or spectroscopy like gas detection there in spectroscopy. And there's also some terahertz imaging going on. Some people want to use 2 lasers, beat them with each other, and generate the terahertz image there to inspect welding systems and material properties. So yes, at TILAS we just make a tunable laser, but the applications are wild, I must say, and I think that's why it's very inspiring to hear you all with the applications in the field. This is the end of my presentation, and it's open for any questions.
Thank you, Dmitry. Then I will kick off a little conversation because, as we're specifically in the 3D sensing meeting, if you had a chance already to work with the partners from the 3D sensing, and what are their specific requirements that they will come to you and say, does it become the coherence left? Does it become the specific wavelength, the power, or other parameters that are like the most important to them? Zach, I will later address this question to you for you to challenge the Dmitry. But Dmitry, first if you have worked with 3D sensing guys, what do they actually ask for?
Yeah,
and where can they sacrifice?
Well, yeah, so that is always a challenge. So thank you for the very interesting question. So if you, for example, look at LiDAR systems, our lasers are not very good in pulse mode, so they need an external pulsar, which we don't have in our systems typically. So we use FMCW LiDAR applications. And the nice thing is when you have a small chirp to do some ranging, the laser can tune to another channel and do the same trick there again. So with a single laser, you can address multiple channels, for example, in the telecom band. And if you have a very simple WDM network, you can address multiple telescopes on your vessel, drone, or whatever you have there to look in multiple directions with a single light source there. So there we find our entrance there. Here for LiDAR, especially the wind LiDAR, you need long distances, and there you need a very stable laser, long coherence length and narrow line width. There, our external cavity is being exploited to the max, and it provides solutions that work with hundreds of meters distance there.
Mm-hmm.
If you go, for example, with this very nice photoacoustic imaging, well, I've got a sketch over here. Is that while making some sound waves into the tissue, the sound waves propagate to the surface of your skin, and you need a microphone array to digest everything there. So here there are multiple systems that scan the region on vibration. It's like a combination with fiber sensing to measure the deflection of the skin and to measure where the sound waves come from. So there you get a lot of in-depth information there. Again, here fast sweeping or fast addressing channels is of key importance for these guys, because the more pixels you can do, the faster you can build up your full image.
Okay, Zach, how about you? So, would you like to challenge Dmitry and ask him for specific things, maybe?
Hopefully not a challenge here, but maybe Dmitry, can you talk maybe a little bit about some of the practical implications or issues, going beyond 1550?
Yeah, so yes, our feedback chip is based on silicon nitride. The technology can be made in other material platforms as well, but a new chip run is an expensive hobby. So at the moment we have the maximum wavelength on the shelf. It goes to close to 1800 nanometers, but there is actually, we just need to rerun a chip in a different platform that supports longer wavelengths. But I don't see a hard stop there. If you go, for example, to 3, 4, 5 micron wavelengths, I think that's easily feasible. But to order a chip and design the chip, that's an expensive hobby. But yeah, I actually see that the longer the wavelength, the easier the platforms work. They suffer less on chip scatter events and other things where lasers are sensitive to. So there I don't see a big issue. And there are material platforms that support longer wavelengths. So I think that's a great asset. Yeah.
So that will, Dmitry, your next guest to the Zach's dust tunnel.
Yeah, exactly.
To see, how far the 1700 penetrates. I have a question about 1550, because one of the selling points of Lumina, right, was the 1550 for the eye, basically eye safety. But in order to get the usable power out of the system, it had to be fiber laser, which become very expensive. What is the story now?
Yeah, so I think very good question. People are always hungry for more photons, and there's a good reason for that. Our lasers are diode lasers, and out of these lasers you get some 40 milliwatts of output power maximum, and then you really end up with an external amplifier to boost the levels to somewhat level of output power. Really multi-watt level that we don't have on the shelf, but watt level can be made fairly easily with amplifier sections behind the laser. So that's the way path forward.
Okay, thank you so much.
I have a question.
Yes, go ahead.
I was kind of curious, Dimitri, actually typically is like there's a little bit of a misconception here. We generally don't need anything better than like about 100 kilohertz. But the big issue is the cost.
Yeah.
What would be a cost point at which you can deliver 100 kilohertz? 20 milliwatts is fine. Power doesn't really matter that much, as you pointed out, because you're going to use an amplifier anyway. So, but the issue is we need to come down to 10 euros.
Yes.
Can you do that?
I think for 100 kilohertz line width, I think that there are some other solutions available which are not relying on hybrid integration. Here we really exploit the low loss part of the silicon nitride, which is just a glass medium, and the amplifier section in indium phosphide or any other material which makes the light there. So this hybrid integration is then offering a narrower line width, which might be overkill for your application. What you say there. These lasers, what you see over here, one offset, the price is about 10,000 euros. If you go to volume,
that would be hard to use.
prices will go down. But if you want for 100 kilohertz line width, I think there are the more affordable solutions on the market. Direct emitters, DFB lasers. Perhaps you compromise a little bit on tuning range, but yeah, I think there's a lot of alternatives available. Yeah.
Thank you.
So I think this conversation is really a polite answer to your question. Well, I will follow up with you. And so, and so we now had and the steering system and chip and the source. Now we need to integrate it all into the one system. And with this, we'll need the last speaker of this session will help us, who is Felipe from Flex Compute. Felipe, the attention of everyone is yours.
Great. It's been a very interesting section. So I'd like to share today some tools that Flex Compute offer that help this industry in designing and optimizing their tools. So Flex Compute is a GPU native platform that will offer simulation solutions for the photonics and other industries. So I would say that, following the analogy, we offer tools that help companies to design the eyes of these sensors. So since we're a GPU native company, we can run the simulations very fast. So bring down the time scale of the simulations from medium to small size structures to seconds. So in 1 hour, you can run hundreds of simulations and quickly optimize some small structures, but it's also very scalable. So we kind of unlock new possibilities for optimization. So we can simulate a very large meta lens, 10 billion grid points in the time scale of 1 hour. That could not be done a few years ago. So you can have a full meta surface for beam steering, for example, and you can optimize the whole structure. You don't need to rely anymore on single unit cells and semi-analytical models. And also offer some very powerful tools for optimization. One of them is inverse design. So the idea of inverse design is that you can have the gradients of a model for a given number, arbitrary number of parameters. So this is an extreme case that each pixel is a free variable and can optimize to produce our logo in the far field. And that together with the scalability, we can have an arbitrary number of parameters and quick optimize a sensor or a component for a sensor. And you have everything integrated with different physics. So you can go in the same workflow, simulate the optics, RF, heat, charge. So this is an example of a avalanche photodiode that you can have everything in the same workflow. So you don't need to go back and forth with different softwares transferring data. It's everything in the same workflow. But the eye is not enough. So actually to see, we need the eye and the brain. So in this analogy, we don't need, we actually need not only the single component, but also a full photonic integrated circuit. And for this task, we offer this tool, what we call Photon Forge. It's a photonic design automation tool that we call. The main advantage is that is integrated with a given foundry PDK. So you can build your layout, use the PDK parametric cells. You can build your own parametric cells. You have auto-routing, auto-detected parts. You can automatically connect components. And it's very powerful because once you have your layout, you can assign models for each one of the components and carry out circuit level simulation. So if you need a full wave simulation of a given component, we automatically build a FTTD simulation using our solvers, solve that for each component and carry out circuit level simulation. So you can characterize with very accuracy a very large and complex photonic integrated circuit like this LiDAR. And I would like to talk about a little bit of what we have been testing today, which is a agentic photonic design. A very interesting feature of Tidy3D is that we are Python native. So we can control all of our solvers with a very well-documented Python API. And we also have very extensive learning resource, hundreds of examples, a lot of documentation, and that's gold for the LLMs. So what I have been trying now is we've placed together an MCP that guides a LLM through our documentation, through our API, so it knows how to use Tidy3D and have plenty of information, many different photonic designs. And you can now just ask for LLM to build a Tidy3D model. But we are going further. We are actually trying autonomous design. So ask the LLM to start with initial design, in this example, this Y splitter, and autonomously trying engineering decisions to optimize that. And it goes autonomously trying different designs until optimize the final design. And this design is pretty good. It reached more than 99% transmittance and was done in about 2 hours autonomously. And this is very flexible. It can be used for different type of problems. We have tried that for auto routing in a photonic chip, for design PN junctions and so on. So it's a very promising tool that have been testing with great success with different type of problems. Well, that's what I have to present today. So any questions and comments are welcome. Thank you.
Thank you very much for being in the room with us today. Flex Compute, you have been supporting Optica in many ways, but today you are really bringing a very interesting topic, which is the use of meta lenses in LiDAR. And when you saw before the LCM structure presented by Lumotive, so the question is very clear. How can you hold them?
I'm sorry?
How can you hold them? They are capable of steering over a wide angular range of 160 degrees. They also can extend this to even 190 degrees beam steering. Is there a way that you could help them going?
This is very interesting. I think our team is already working with Tidy3D in some ways. So,
so the question goes back to you, Apurva. How can you
Yes,
challenge them? What do you need from them?
yeah, I think from our semiconductor side, we are very impressed with the capabilities that Tidy3D is bringing. It's not easy to simulate so many different pixels and and over the entire surfaces. So honestly, I personally don't know the details, but I know that my team is pretty happy with what they're seeing from the simulation environments that they're producing. So we're looking forward to more collaboration.
I'm looking forward to more collaboration with you, Philippe, from Flex Compute. Apurva, you have been great today at the meeting. I would like to also say that my very good friend Rimos has been great, and Hendrik. But I would like to go to Zach once again for the closing remark. Zach, you have heard today about point cloud. You have heard today about the SCM of Lumotive. You have heard about the simulation of Flex Compute. What is this idea that you go now with?
Yeah. I think one of the things I walk away from, learning is just really about the whole ecosystem, right? That goes into developing, especially these LiDAR devices, and how the whole ecosystem is becoming more mature, right, and evolving. It's not something that I follow that deeply, right, on a day-to-day basis. So it's fun to come into a forum like this and do a deeper dive and understand how it's evolving, and how just gives me an impression that this technology is going to have a very important role to play, right, in our equipment moving forward. And that maybe we're just really kind of starting to scratch the surfaces of the capability, and excited to see how it's going to continue to evolve.
Zach, let's make a deal. If you need the lasers from Chilas, from Dimitri, or you need the development kit of Remus, I pay for the shipping expenses, and I don't even charge it to Optica.
Okay.
I put it in my own pocket.
I'll
Thank
hold
you
you
very
to that,
much,
Jose.
everyone, for a fantastic meeting.
Thank you, Jose.
This is Optica. This is lighting redefined.
All right, allow me to ask my IT department to cut the live stream. Cut it, because I don't want anybody to see me undoing my time. Thank you.